Hello, I am Matthew Wright, postdoctoral fellow at the Institute for Mathematics and its Applications. In this video, I give an introduction to persistent homology, a popular tool in topological data analysis and a subject of my research. Persistent homology is an algebraic method of discerning the topological features of data. By topological features, I mean things like components, or clusters, and holes. Data can be, for example, a set of points with a metric that gives distances between pairs of points. For example, consider the following point cloud, consisting of 19 points in a plane. What topological features does the data exhibit? It appears that these points were roughly sampled from an annulus. But how can we detect the annulus from the points alone? The problem is that discrete points have trivial topology. One idea is to connect nearby points. We first choose a distance, or scale parameter, d. We draw a ball of diameter d around each point. Two balls intersect exactly when 2 points are no further apart than distance d, in which case we connect the 2 points with an edge. This creates a graph whose vertices are the original points. The graph shows us that the points form a single cluster at scale parameter d, but it doesn't tell us about higher order features such as holes. For example, this graph has many cycles, but the graph doesn't help us identify the central hole in the data. To introduce a more sophisticated idea, we need a bit of background information. First, a simplicial complex is an object built from points, edges, triangular faces, and so on. A point is a zero-dimensional simplex. An edge between 2 points is a one-dimensional simplex. A triangular face is a two-dimensional simplex. A solid tetrahedron is a three-dimensional simplex, and so on for higher dimensional simplices. If we glue many simplices together in such a way that the intersection between any two simplices is also a simplex, we obtain a simplicial complex. Here is an example of a simplicial complex. In topology, we define something called homology for simplicial complexes. While the formal definition of homology is a bit too technical for this video, we can think of homology as counting the connected components, holes, and voids of a simplicial complex. Moreover, homology is computable via linear algebra. To learn more about homology, consult your nearest algebraic topology textbook. Okay, back to our point cloud. Let's connect nearby points and then build a simplicial complex. We start with a distance d, as before, and connect pairs of points that are no further apart than d. This time, however, we fill in complete simplices. That is, if we see 3 points connected by edges that form a triangle, we fill in the triangle with a two-dimensional face. Any 4 points that are all pairwise connected get filled in with a 3 simplex, and so on. The resulting simplicial complex is called the Rips complex, or the Vietoris-Rips complex. We then apply homology to this complex, which reveals the presence of the central hole. There is still a problem, however. How do we choose the distance d? If d is too small, we might see multiple connected components and small holes that are artifacts of the sampling. In short, we detect noise. On the other hand, if d is too large, then any 2 points get connected, and we get a giant simplex, which has trivial homology. We don't know what distance to choose without some special insight. This choice of d reveals a single hole, but how do we know it is significant and not noise? Rather than choosing a single distance d, we consider all distances d. Observe that each hole appears at some particular value of d and disappears at another value of d. For example, consider these 4 points. There is some smallest distance, this d1, which is just large enough for these 4 edges to appear, creating a hole in the middle. For the same configuration of points, there is another distance, this d2, which is just large enough for an edge to appear between opposite points. This completes 2 triangles that get filled in, and the hole disappears. So the hole appears at distance d1 and disappears at distance d2. We can represent the persistence of this hole as a pair, d1, d2. We can also visualize this pair as an interval, or bar, from d1 to d2. This bar is a visual representation of the persistence of the hole. A collection of such bars is called a barcode, and barcodes are a central object of study in persistent homology. Let's return to our point cloud example. We will create growing balls around each point and record the barcode. As the balls start to grow, edges begin to appear, and the complex gradually becomes connected. A few small holes appear, but quickly become filled in. The large central hole appears, and remains as more and more two simplices appear around the outside. Eventually, as the balls get large, Edges appear across the center of the hole, and it eventually gets filled in as well. Now, rewind the movie and play it again. The small holes that appear first are due to sampling irregularities, or noise, and are represented by short bars in the barcode. The large hole, which we regard as a significant feature of the data, is represented by a long bar in the barcode. This is the general interpretation of barcodes. Short bars represent noise, long bars represent features. A key property of barcodes is that they are stable under perturbations of the data. In other words, if you adjust the points a little bit, the barcode only changes a little bit. This stability is important in applications in which measurements always have some margin of error. Persistent homology is also computable via linear algebra. Standard algorithms exist to compute barcodes. The worst-case runtime of these algorithms is cubic in the number of simplices, although the computation is rarely worst-case. In addition, clever data structures and topological simplification can speed up the computation significantly. Persistent homology has been applied to various problems. For example, Carlsson and others studied the collection of high-contrast patches, 3 by 3 pixels in size, from a large set of grayscale photographs. Treating the patches as 9-dimensional vectors and applying persistent homology, they found that the resulting point cloud was close to the surface of a Klein bottle embedded in a higher dimensional space. This observation is useful for image recognition applications. For another example, Perea and others use persistent homology to detect periodicity in time series data. Using sliding window embeddings, the researchers converted measurements of a periodic signal into a point cloud in a high-dimensional space. Persistent homology applied to the point cloud detects cycles, which correspond to periodicity in the original signal. Applying this methodology to gene expression time series data, the researchers detected periodicity that was missed by other methods, especially periodicity in the presence of damping. Persistent homology has been studied extensively from an algebraic perspective. Specifically, a barcode is really a visualization of an algebraic structure. In our barcode animation, we were really dealing with a sequence of simplicial complexes, each a subcomplex of the next. That is, the simplicial complex constructed from the data for some small distance is a subset of the simplicial complex constructed for a larger distance. Equivalently, there is an inclusion map from each simplicial complex to the next. This sequence of simplicial complexes with inclusion maps is called a filtration. When we apply homology to a filtration, we obtain an algebraic structure called a persistence module. Suppose we want to compute ith homology with coefficients from a field K. The homology of any complex Cj is a vector space, and the inclusion maps between complexes induce linear maps between homology vector spaces. The direct sum of the homology vector spaces is an algebraic module. In fact, a graded module over the polynomial ring K adjoin X. The variable X acts as a shift map, taking each homology generator to its image in the next vector space. Furthermore, a structure theorem tells us that a persistence module decomposes nicely into a direct sum of simple modules, each corresponding to a bar in the barcode. In other words, a barcode really is an algebraic structure.
Persistent homology is a fascinating mathematical tool that continues to be studied, developed, and applied. To learn more, consult the papers and books by Carlsson, Edelsbrunner, Ghrist, and others. Or see my website to learn about my work in multidimensional persistent homology. Thank you for watching this video. I am Matthew Wright.